Okay, so this last section of chapter 22 has to do with the spectrochemical series. And so you might have been wondering, well, what makes some coordination compounds high spin and what makes some low spin? How do we know the magnitude of the crystal field splitting energy? And the answer is it depends on the ligands themselves. So some ligands are going to cause wider energy splittings, and some ligands are going to cause smaller energy splittings. And so it all has to do with the ligands themselves. So the spectrochemical series is what we call the arrangement of ligands from what we call weak-filled ligands over here. So fluorine, bromine, chlorine, azido, which is the N3 minus. These are ligands which will cause small splittings in the d orbitals energy levels and lead to high spin coordination compounds and complex ions. And then over here, you've got things like cyano and carbonato. They're going to cause big splittings in the d orbitals that will lead to low spin complexes. So let me just make sure we get everything straight here. So I'll draw it on this side, sorry. I want to make sure I'm not backward here. Okay, so a strong field ligand is going to lead to a large delta. Sorry, let me get rid of this. Just realized you can't see. A strong field ligand is going to lead to a large delta, and that's going to lead to low spin complexes. And then a weak field ligand is going to lead to a small crystal field splitting energy and high spin complexes. And so just keep that straight. This the spectrochemical series here isn't something that you need to memorize. And it's actually kind of hard to make any inferences about like what structural features of a ligand might make something strong field or weak field. I'm sure there is some sort of a pattern there, a way to maybe predict whether a ligand will be strong field or weak field, but I don't know what it is, and I would just refer to this figure or a similar list in order to determine. And then also things can get complicated for coordination compounds or complex ions which have different ligands, right? Maybe you have some strong field and some weak field ligands. In fact, maybe their position is going to affect things. So if you had strong field ligands in a cis conformation or in a trans conformation, maybe that'll affect things. I don't know. It could get pretty complicated. So we're just going to investigate the simple cases where everything can be neatly divided up into either a high spin or a low spin complex. Most electronic transitions are in the ultraviolet range, but D to D transitions are relatively low in energy. Again, these crystal field splitting energies are similar to like the energy required to pair an electron with an already occupied orbital. So these are relatively small energies compared to other electronic transitions. And so that means that for coordination complexes, let me just draw one up here real quick. Let me, I think we have the time, let me just quickly make an analogy, right? So oxygen is going to have the sigma 2s, the sigma 2p, the pi 2p, pi star 2p, and the sigma star, I left one off, sorry, sigma star 2s, sigma 2s, and the sigma star 2p. And if we look at oxygen, how many valence electrons should it have? It should have 12. So 6 from each oxygen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And we call this the HOMO, the highest occupied molecular orbital, and this the LUMO, the lowest unoccupied molecular orbital. And the wavelength of light that would be absorbed had to do with the HOMO to LUMO gap. How much energy does it take to move an electron from the HOMO to the LUMO? Anyway, this is all a review of molecular orbital theory. And these energies for molecules like O2 are going to be ultraviolet. They're going to require a lot of energy, short wavelength of light, etc. So for coordination compounds, instead what you'll have, let's do a tetrahedral, high spin compound with 4 electrons. Okay, it's tetrahedral, so I put 2 on the bottom and 3 on top. It's got 4 electrons, and that's just a number I made up. I said it was high spin, sorry, did I say high spin? I meant low spin. It is a low spin compound, and so I paired up those electrons instead of putting 2 up here. And so what we're looking at is how much energy would be required to promote an electron from that T2 to the E energy level. And that's going to be a relatively small amount of energy. So we can say delta E, the crystal field splitting energy, is equal to hc over lambda. And this is again a review, right? So a photon of light is going to have an energy that depends on its wavelength. H is Planck's constant. That's 6.626 times 10 to the negative 34th joule seconds. C is the speed of light, 2.998 times 10 to the 8th meters per second. And we can find lambda, the wavelength, if we know the crystal field splitting energy. Or we can find the crystal field splitting energy if we know the wavelength of light that is absorbed by the compound. So the observed color of the compound, we can observe the color in 2 different ways. Sorry, one moment here. The first is if we have a high enough concentration and things, then we can just look at it. A lot of these compounds will be vibrantly colorful to the naked eye. And so if I see a compound and it is a bright blue, then what that actually means is that the crystal field splitting energy is going to correspond to light of 600 to 500 nanometers, or about 600 nanometers of wavelength. You'll notice that's on the opposite side of blue. So if 600 nanometer light is absorbed by the complex, then blue is what I will see, because that's the light that gets through, that escapes. And so if you're looking at the actual color of a compound by the naked eye, then you're going to want to choose the wavelength that is opposite of that. If I have a red compound, that is that's about 700 nanometer wavelength of light, is the color red. But I would actually want to go to the opposite of that. Maybe something like 515 nanometers would be the wavelength which corresponds to the crystal field splitting energy. Okay, and the other way to do is to actually take an absorption spectrum. And so here we've got a plastocyanin complex. It's a protein, and it absorbs light at 595 nanometers. If we'll look at the color wheel, that's orange, and plastocyanin actually looks blue to the naked eye. And let's go ahead and take that 595 nanometers and figure out what is the crystal field splitting energy for plastocyanin. We got a new chalk. So we can rearrange this. Oh no, we don't need to. So delta E is going to equal 6.626 times 10 to the negative 34th joule seconds times C 2.998 times 10 to the 8th meters per second over the wavelength of, what was it, 595 nanometers. So that's going to be 595 times 10 to the negative 9th meters. No decimal there. This is just my really quick way of knowing how to punch the numbers in to my calculator. And I didn't plan on doing this problem, so I don't actually have my calculator in here, but I'll show you my computer calculator once it gets booted up. Oh, there it is. Okay, so what do I have? 6.626 E negative 34 times 2.998 E 8 divided by 595 E negative 9. And what I get is 3.3 times 10 to the negative 19th. So our crystal field splitting energy, 3.3 times 10 to the negative 19th joules. We probably get 3 sig figs, so 3.34 times 10 to the negative 19th joules. That is the crystal field splitting energy. Okay, we'll turn that off. All right, one last thing to talk about, and that is magnetic properties. Again, this is very analogous to what we talked about with molecular orbital theory. So you're familiar with ferromagnetism. That's the magnetism of a refrigerator that a magnet sticks to with great force. But actually every substance, and I do mean every substance, is going to experience some sort of a force in the presence of a magnetic field. And so I'll write down ferromagnetism. Ferromagnetism is just ordinary magnetism. There's only a handful of metals that exhibit ferromagnetism, and it's the magnetism that you're used to. But there's also paramagnetism. And paramagnetism, or paramagnetic materials, they are weakly attracted to a magnetic field. It's not nearly as strong as a refrigerator magnet. It's not going to hold up any children's art to the refrigerator wall, but it can be measured. It can be observed in the lab. So paramagnetism is weakly attracted to a magnetic field. And then here's the weird one. Diamagnetism is weakly repelled by magnetic fields. It's like an anti-magnet. And it's also weak enough that it's not anything that you'll experience in everyday life. But if you have sensitive laboratory measurements, you can feel the repulsive force between a diamagnetic material and a magnetic field. Now, how do we know what a compound is going to be? Well, paramagnetism is going to have unpaired electrons. well, at least one or more unpaired electrons. Diamagnetic materials will have all electrons paired. And so we already applied these ideas in the context of molecular orbital theory. Well, let's now consider the compound ZnCl4. So this has a Zn4 plus cation. And zinc, let me, I wonder if I can pull up a periodic table. Sorry, give me just a second here. Yes, I did have that ready to go. All right, so you can see zinc is at the end of the D block, and so zinc's electronic configuration is going to be the argon core with 4s2 and then a 3d10. But the zinc 4 plus is going to lose 4 electrons, and so it'll lose 2 of those 4s electrons first, and then lose 2 of the 3d electrons, and so it'll be left with 8 electrons. So zinc ion's electronic configuration is argon 3d8. So we have 8 electrons to deal with. Oops, wrong one. Go away, periodic table. Okay, so 3d8 is the electronic configuration. Zinc, ZnCl4, this is an octahedral complex, and so that means that we'll have the 3 orbitals in the lower energy level and 2 orbitals in the upper energy level. And let's look at both the high spin and the low spin case here. We have 1, 2, 3, 4, 5, 6, 7, 8. You know what? Have I done something wrong? I must have. Let's not have it be zinc. Let's have it be... I'm so sorry. I chose the wrong metal. It was supposed to be nickel. Can I undo all this? What a mess. Okay. Yeah. So nickel chloride will have nickel 4 plus, and nickel's got 2 fewer electrons than zinc, so we would have 3d6. That's the problem that I meant to do. And so for a low spin complex, the electrons would be organized in this way. For a high spin, the electrons would be organized in this way. 1, 2, 3, 4, 5, 6. Now think back to the the spectrochemical series, and the chloro ligand was far onto the weak field end. That means it's going to make high spin compounds, so we would expect this compound to be paramagnetic, that is weakly attracted to a magnetic field, and indeed it is. So that is it for chapter 22. Sorry, some of these last examples were a little bit botched. I thought I was prepared for this, and I made a couple of little mistakes in my notes, so I apologize for that. But I hope it got the point across.